Hello everyone, I'm Reena, an employee at Tata Steel. Time for a pre-test before you get into the course. Hello all. Welcome to the e-learning course on heat treatment of steel. I'm Reena, an employee at Tata Steel. Working here, I often remember the quote Richard M. Nixon once quoted, "The finest steel has to go through the hottest fire." Needless to say, heat treatment plays a vital role in the production of steel. This e-learning course will help you understand it better. With me is Smita, an expert in heat treating techniques. Let's approach her and understand the various concepts involved in heat treatment of steel. Hi Smita, I'm glad that you're with us. With all the knowledge you possess, we are sure that you will add value to our learning. Definitely, Reena. Let's get started. Click Next to proceed to the next screen. With the help of this course, you will be able to explore the following topics: material structure of steel, heat treatment of steel, TTT diagram, CCT diagram, heat treatment techniques. Click Next to proceed to the next screen. We shall begin the course by understanding what the material structures of steel comprise of. Material structures can be broadly classified into three types, namely macrostructures, microstructures, and crystal structures. Macrostructure is the gross structure of a material as visible to the unaided eye or at very low levels of magnification. Microstructure is the structure of a material as revealed by microscopy. Main structural information which are to be taken into consideration are microstructure and crystal structure. Click Next to proceed to the next. Structural information of steel can be estimated through a pictorial diagram called phase diagram. Phase diagram is equilibrium diagram of different phases appearing at different temperatures, and if we change the composition, phase fraction would change as well as different phase might appear. Steel is a family of iron carbide, alloys and other alloying elements like manganese, silicon, chromium, vanadium, molybdenum, etc. Taking a look at the iron carbide phase diagram, we can observe that at 0.8% carbon above A1 line, steel is at austenite phase and has distinct microstructure or grain structure. On cooling below A1 temperature, it transforms into 100% pearlite, which is a phase mixture of alpha iron and cementite. Cooling a composition less than 0.8% carbon above the A3 line structure would be different, as we would come across to Eutectoid ferrite at austenite grain boundary and pearlite in rest of the grains. Hence, it is evident that if we change the composition, structure would change accordingly. Click Next to proceed to the next screen. As we have previously seen, microstructure of steel varies at different phases. Let us now understand this in detail by clicking on each of the tabs. Austenite grains. Austenite is an interstitial solid solution of carbon in iron having Mpsc crystal structure. Its microstructure is usually large-grained, depending upon microalloy addition. Ferrite grains. Ferrite is an interstitial solid solution of iron and carbon having very low solubility and its crystal structure is BCC. Pearlite. Pearlite grains have lamellar structure of alpha ferrite and cementite, where dark lines are cementite and white regions are alpha ferrite. We have seen in the phase diagram how microstructure and crystal structure change with the composition. But are they interdependent? I think we should approach Smita in order to understand further. Hi Smita, I have a doubt.
Hi Reena. Yes, tell me, how can I help?
Could you please explain how composition is dependent on properties, performance, processing?
Sure Reena. Look at this. A material tetrahedron depicts interdependent relationship among the structure, properties, performance and processing.
Okay. How are these properties interdependent?
Property will decide what the performance would be. If we change the processing without changing composition, we can get different properties and accordingly we can have different performances.
Okay.
So, as you see, heat treatment is all about processing. Processing includes phase transformation, thermodynamics, and kinetics.
I now get it. Thanks, Smita, for the detailed inputs. I shall again take your help, if required. Click. There are two main types of transformation diagrams that are helpful in selecting the optimum steel and processing route to achieve a given set of properties. These are time temperature transformation (TTT) diagram, typically a C-shaped curve, and continuous cooling transformation diagram. The TTT diagram gives the kinetics of phase transformation. It is also called isothermal diagram. TTT diagram explained what should be the temperature and time required to achieve a particular structure and accordingly particular property. Percentage of transformation is given by the formula function of IU, where I represents growth rate and U represents nucleation rate. Note, the development of the microstructure with time can be followed by holding small specimens in a lead or salt bath and quenching them one at a time. After increasing the holding times and measuring the amount of phases formed in microstructure with a microscope, let us understand the TTT diagram further in detail. In order to understand the TTT diagram, we must first understand the nucleation and growth kinetics. Let us now see how they work. Phase transformation take place by nucleation followed by growth. After formation of stable nuclei, its growth occurs until equilibrium phase is being formed. Growth occurs in two methods: thermal activated diffusion, controlled individual atom movement, or a thermal collective movement of atoms. First one is more common than the other. If we plot fraction phase transformation versus time, the curve will be typically an S-shaped one. Let us suppose for temperature T1, which is just below A1 temperature, we keep the sample for long time. Transformation will not start immediately. It will start after some time, which is called incubation period. In this condition, undercooling is low, so there is less driving force for nucleation. Thus, incubation period is higher. After nucleation, growth of transformed phase has taken place, fraction transformed phase will rise. This is a typical behavior of diffusional oriented transformation. At T2, where T2 is less than T1, driving force is higher. Thus, incubation period is less, and the transformation behavior would be same as in first case. Click next to proceed to. You have seen how a TTT diagram looks like. Ever wondered why it is C-shaped? Let us understand why. Overall transformation rate is a function of both nucleation rate and growth rate. However, these two factors are again temperature dependent. If a plot of temperature versus rate of transformation is plotted, the curve will look as shown on the screen. Now, if we convert the diagram in temperature versus time, we will get an invert curve. Thus, the TTT curve looks like C curve. At very high temperature, undercooling is very low. Hence, transformation rate would be very slow. At very low temperature of undercooling is high, that is, driving force for nucleation is high. Due to low temperature, diffusion rate would be very slow, and thus growth would be sluggish. Only at intermediate temperature, both nucleation and growth will be very fast or significant. Only there, the transformation rate would be maximum. Hope this information has been useful. Click next to proceed to the next screen. So we have seen how TTT diagram is useful in studying the kinetics of phase transformation. Now in this topic, we will see phase transformation kinetics of three compositions of steel. I think I know a little bit of this, but I'm not very sure. Wow, Smita is coming. Let's take her help. Hi Smita, you are just in time. I was thinking of coming to you. Hi Reena. Oh good. Is there anything I can help you with? Yes, about the C-phase transformation, kinetics of three compositions of steel. Okay, so think and tell me what are the compositions? I think that these phase compositions are: number 1, Eutectoid steel, which has 0.83% of carbon by weight. Number 2, hyper Eutectoid steel, which has 0.22 to 0.83% of carbon by weight. And number 3, hyper Eutectoid steel, which has 0.83 to 2.14% of carbon by weight. Absolutely right. You know it. Also, Reena, here it is important to note that
The temperature at which the phase transformation of steel gets started or completes is known as its critical temperatures. Oh, okay. Please tell about critical temperatures a bit. Sure. Look at this diagram, Reena. There are 3 critical temperatures in steel heat treatment process. They are temperature A1, that is 727 degrees Celsius. At this temperature, austenite begins to form during heating. It is also known as Eutectoid temperature, and sometimes it referred to as the lower critical temperature. The second critical temperature is A3, that is 910 degrees Celsius. It is referred as the upper critical temperature. And the third critical temperature is ACM. It is the temperature at which the solution of cementite in austenite is completed during the heating process in hyper-eutectoid steel. I see. Please go ahead. Let us now discuss about eutectoid steel, where the phase transformation takes place below lower critical temperature. The schematic representations of the microstructures for an iron-carbon alloy of eutectoid composition and above and below the eutectoid temperature is shown at the screen. As you can see above 727 degrees Celsius at 0.83% of carbon by weight. The structure of steel is austenite at point A along XX- composition line. As we cool the steel below lower critical temperature, A1, the structure changes to pearlite at point B along XX- composition line. That's really interesting, and I think it's even more clear because you have explained it well. Thank you. I need to rush for a meeting. Let me know if I can be of any further help. Sure, Smita. Thanks once again.
Well, that was quite a learning from Smita. But there is still more to go. Now let us look at phase transformation kinetics through transformation of TTT diagram under isothermal conditions, that is, keeping the steel sample at under cooling condition for a long time. The phase transformation takes place at temperature T1, where T1 and T2 are phase transformation start time and finish time. Now let us look at phase transformation at temperature T2, which is at a higher undercooling temperature. Here T3 and T4 represents phase transformation start time and finish time. It is important to note that here transformation will start earlier as compared to T1 due to higher undercooling. In this way, we could have multiple number of start and finish points from different undercooling period where the rate of transformation is just C curves, and somewhere in between we could also find 50% transformation curve. At the nose of C curve, T0 is shown the minimum incubation period where the rate of transformation is maximum. Just above the nose, the transformed product is pearlite, and just below the nose, the transformed product is bainite. Pearlite and bainite are formed by the mechanism of carbon diffusion. These are time-dependent transformation and known as reconstructive transformation product, whereas another product formed named as Martensite, which is displacive in nature. Here Ms and Mf represents Martensite start temperature and finish temperature. Transformation of Martensite is not reconstructive, it is athermal. That is, if we cool below temperature, Ms, say at 5% transformation, and place it for long time, then Martensite finish will not take place, and final structure will be 5% Martensite plus retained austenite. Hardness increases as the transformation temperature decreases. Here we find 3 different structures at different cooling conditions. Click next. Having learned about phase transformation of steel under isothermal conditions, let us now take a look at how phase transformation of steel takes place under a range temperatures. As you can see in the phase diagram here, phase transformation at temperatures between approximately 705 degrees Celsius and 535 degrees Celsius result in the characteristic lamellar microstructure of pearlite. At a temperature just below A1 line, nucleation of cementite from austenite will be very slow, but diffusion and growth of nuclei will maximum speed, so that there will be few large lamellae and the pearlite will be coarse. However, as the transformation temperature is lowered, that is, it is just above the nose of the C curve, the pearlite becomes fine. At high temperature, while undercooling is low, coarse pearlite is formed. At the nose temperature, fine pearlite and upper bainite is formed. Bainite is also a mixture of ferrite and cementite, but not in the form of alternate layers, rather in the form of needle type. Bainite formation temperature range is 535 degrees Celsius to 230 degrees Celsius. On the other hand, Martensite transformation is a diffusion-less process. It forms below 230 degrees Celsius, where rapid changes in temperature cause shear displacement of atoms and individual atomic movements of less than 1 inter-atomic spacing. The transformation is a sudden and systematic shifting or shearing of iron atoms into a body-centered tetragonal structure. Click next. You have seen the phase transformation of steel under different conditions. You have also learned that during the phase of transformation process, different microstructures of steel are formed. Now we will learn more about these microstructures. Click on each tab to learn more. Pearlite. There are two types of pearlite, namely coarse pearlite and fine pearlite. Just below the eutectoid temperature, a relatively thick layer of both the ferrite and Fe3C phases are produced. This microstructure is called coarse pearlite. At these temperatures, diffusion rates are relatively high. Carbon atoms can diffuse relatively long distance, which results in the formation of thick lamellae. With decreasing temperature, the carbon diffusion rate decreases, and the layers become progressively thinner. The thin layer structure produced in the vicinity is termed as fine pearlite. Bainite. The microstructure of bainite consists of ferrite and cementite phases, and thus diffusional processes are involved in its formation.
We have learned in the previous topic that a hypo-eutectoid steel alloy has 0.22 to 0.83% of carbon by weight. Now we will analyze the iron-carbon diagram showing hypo-eutectoid composition. Looking at the diagram, at point C along Y to Y dash composition, line structure of steel is completely austenite. On cooling in dual phase region, at point D, pro-eutectoid ferrite starts nucleating at prior austenite grain boundary. At point E, growth of pro-eutectoid ferrite seen along grain boundary. At point F, below lower critical temperature, final microstructure appears as mixture of alpha ferrite plus pearlite. Click next to diagram
of hypo-eutectoid steels. The TTT diagram for hypo-eutectoid steels will have an additional curve to show the precipitation of pro-eutectoid ferrite from austenite before the remaining austenite is transformed to pearlite. As the carbon percentage increases, A3 decreases. That is, austenite stabilizes. So the incubation period, T0, for the austenite to pearlite increases. That is, the C curve moves to right. The image shown here is the micrograph of hypo-eutectoid steel, where colonies of pearlite and primary ferrite or pro-eutectoid ferrite are visible. So you may be wondering, what is this pro-eutectoid ferrite? You see, pro-Eutectoid ferrite is the ferrite that forms at the Austenitic grain boundary, because Austenitic grain boundary has an easier diffusion path. It tends to grow more rapidly along the austenite grain boundary and not within the grain.
Click next. Covered a lot, but there is way more to go. In the previous topics of this course, we have analyzed the TTT diagram of eutectoid and hypo-eutectoid steel. You are now in the fifth topic of this course, TTT diagram for hyper-eutectoid steel. A hyper-eutectoid steel alloy has 0.83 to 2.14% of carbon by weight. Now we will analyze the iron-carbon diagram showing hyper-eutectoid composition as it is cooled from within the austenite phase region to below the eutectoid temperature. Look at the diagram. At point G, along ZZ- composition line, the structure of steel is completely austenite. On cooling in dual phase region at point H, pro-eutectoid cementite starts nucleating at prior austenite grain boundary, and at point I, below lower critical temperature, the growth of pro-eutectoid cementite is seen along the grain boundary. Thus, the final microstructure appears as a mixture of cementite and pearlite. Click next to proceed to the next screen.
Let's look at the TTT diagram of hyper-eutectoid steels. The TTT diagram for hyper-eutectoid steel differs from that of eutectoid steels. The TTT diagrams for hyper-eutectoid steel will have an additional curve to show the precipitation of cementite from austenite. This happens from the transformation of remaining austenite to pearlite. With any increase in carbon content above the 0.83%, the ACM line goes up. That is, austenite become less stable with respect to cementite and starts participation. So with this, the transformation to pearlite becomes faster. Therefore, the C curve moves towards left after crossing the 0.83% of carbon content. The image shown is the micrograph of hyper-eutectoid steel, consisting of a white pro-eutectoid cementite network surrounding the pearlite colonies. Pro-eutectoid cementite is a very small volume fraction of cementite nucleate at the austenite grain boundary, and it grows along the grain boundary, as grain boundaries are most unstable areas and have lot of vacancies. Click next to proceed to the next screen. Look at the various types of TTT diagrams. Let us now summarize the iron-carbon diagram and TTT diagrams. Figure A depicts the portion of iron-carbon diagram showing isothermal transformation of supercooled austenite at different temperature, also showing a thermal transformation to martensite. For hypo-eutectoid steel above A1 727 degrees Celsius temperature, austenite partially transforms to ferrite, but at below A1, austenite initially transforms to ferrite, enriching the remaining austenite with carbon, which at a later stage transforms to pearlite. At its composition enters the marked area pearlite. Similarly, for hyper-eutectoid steel, austenite transforms to free cementite and pearlite below A1 temperature. If austenite is supercooled to regions marked pearlite or bainite, it fully transforms to either of these two products. Supercooled austenite below Ms temperature transforms to martensite athermally. Figure B represents the TTT curve of hypo-eutectoid plain carbon steel. Figure C represents the TTT curve of eutectoid plain carbon steel. Figure D represents the TTT curve of hyper-eutectoid plain carbon steel. The points to be noticed here are: Ms temperature is different for all three compositions. Nose of curves also is a function of percent carbon in steel. Click next to proceed to the next screen. You might have got an idea about the TTT and CCT diagrams. Now we will make a comparative study of both of them. As you can see, the diagram shown on the screen is a TTT diagram. Now you will see a red curve which is shifted to the right of the TTT curve. This curve is known as the CCT curve, as the continuous cooling transformation occurs at lower temperature and for a longer time compared to the isothermal holding. It is interesting to note that bainite generally does not form steels during continuous cooling, and hence the CCT curve ceases just below the nose. The microstructure of steel, whether fine or coarse, depend on the cooling rate. Higher the cooling rate, finer the microstructure. Now look at the curve C. It is at tangent to the nose of the TTT curve. It is important to note that the cooling rate associated with this cooling curve is called as the critical cooling rate for this steel. Look at the curve A. It represents the annealing process, wherein the steel is heated in the gamma region and is very slow cooled in the furnace. This process produces coarse pearlite. Now shift your attention to the curve B. And hence the CCT curve ceases represents the hardening process. In this process, the steel is heated in the gamma region and is then quenched in water. Here, the cooling rate is greater than the critical cooling rate. This process produces martensite as it requires a cooling rate higher than the critical cooling rate. So the bottom line of our discussion is that while keeping the composition of the steel same, if we change the processing conditions, we could get different microstructure and hence their properties will also differ accordingly. In the next topic, we will learn about the different heat treatment techniques. Click next. Previous topics of this course, we have seen how processing conditions play an important role in producing different microstructures of steels. These processing conditions can be called as heat treatment techniques. Now in this topic, we are going to learn about these heat treatment techniques in detail. Let us understand more about them from Smitha. Hi Smitha.
Hello, Reena.
Could you please tell us more about the heat treatment techniques?
Sure, Reena. The 5 important heat treatment techniques are annealing, normalizing, hardening, tempering, spheroidization.
Okay, please explain them further.
The first heat treatment technique is annealing. Annealing is a generic term denoting a treatment that consists of heating to a holding at a suitable temperature followed by cooling at an appropriate rate, primarily for the softening of metallic materials. Generally in plain carbon steels, annealing produces a ferrite-pearlite microstructure.
Okay.
Steels may be annealed to facilitate cold working or machining, to improve mechanical or electrical properties, or to promote dimensional stability. The iron-carbon binary phase diagram can be used to better understand annealing processes.
Okay, so why is the process of annealing required?
That is a good question. Talking about annealing, we also need to understand the purposes of annealing. Annealing process is used to remove residual stresses, improve toughness, restore ductility, refine grain size, enhance machinability, eliminate chemical non-uniformity.
Interesting. Annealing has a lot of uses attached to it. Thanks for the input, Smitha. They were indeed insightful.
My pleasure, Reena.
Click next to proceed to the next screen. We have learnt about the annealing process. Now let us take a look at annealing cycle. In practice, thermal cycle of almost infinite variety are used to achieve the various goals of annealing. These cycles fall into several broad categories that can be classified according to the temperature to which the steel is heated and the method of cooling used. These are 3 important annealing cycles. They are subcritical annealing, intercritical annealing or partial annealing, and full annealing. Under subcritical annealing, the material is heated up to a temperature just below the lower critical temperature A1, whereas intercritical annealing or partial annealing is where the material is heated above the lower critical temperature A1, but below the upper critical temperature A3. But under the full annealing process, the material is heated above the upper critical temperature A3. We will learn about each of them in detail in the next screen. Click next. As discussed, There are three important annealing cycles. The three categories under annealing cycles, namely subcritical annealing, partial annealing, and full annealing, are displayed on the image. Click on each of them to learn more. Full annealing. A common annealing practice is to heat hypo-eutectoid steels above the upper critical temperature to attain full austenization. This process is called full annealing. Partial or intercritical annealing. In the continuous annealing process, an intercritical annealing practice is used to develop dual-phase and tri-phase microstructures. In this practice, the steel is rapidly cooled from the intercritical temperature. The rapid cooling results in the transformation of the pools of austenite to martensite. Subcritical annealing. Subcritical annealing does not involve formation of austenite. The prior condition of the steel is modified by thermally activated processes such as recovery, recrystallization, grain growth, and agglomeration of carbide. The prior history of the steel is, therefore, an important factor in as rolled or forged hypo-eutectoid steels containing ferrite and pearlite. Subcritical annealing can adjust the hardness of both the constituents, but excessively long times at temperature may be required for substantial softening. The treatment technique and hence require furnaces to carry out the process. Furnaces used for annealing are of both basic types, namely batch furnaces and continuous furnaces. Click on Well, by now, you have got a good understanding of the annealing process. Now we will learn about annealing of the cold rolled steel. Increase in ductility. Strain. Well, to proceed to the next screen, images shown here are the most structures of cold work. Now we will learn about the grain structure. The two images shown here are the most structures of cold work steel before and after annealing. Annealing of the cold rolled steel normally is designed to produce a recrystallized ferrite microstructure from the highly stressed grains resulting from cold work. Click Next to proceed to the next screen. Annealing models were developed for the production of cold spots within the coils and also in the stack. The heating times were controlled by maintaining the difference between the hot spot and cold spot temperature. The annealing heating time and soaking time is said to be over once the cold spot reaches the set temperature. Click Next to proceed to the next screen. We have learned about annealing process and its various types. Now we will learn about the second important heat treatment technique, normalizing. Normalizing is used to refine grains to produce a uniformly distributed fine-grained pearlite steel, which are tougher than coarse-grained pearlite steel, is produced in annealing process. Normalizing is the process of raising the temperature to over 60 degrees Celsius or 108 degree Fahrenheit above the A3 or ACM line fully into the austenite range. It is held at this temperature to fully convert the structure into austenite, and then it is removed from the furnace and cooled at room temperature under natural convection. This results in a grain structure of fine pearlite with excess of ferrite or cementite. This process is considerably cheaper than full annealing since there is no added cost of controlled furnace cooling. A partial iron carbide phase diagram is showing typical normalizing range for plain carbon steels is displayed on the screen. As you can see, normalizing is accomplished by heating the steel at least 60 degrees Celsius above the upper critical temperature A3 for composition less than the Eutectoid and above ACM temperature for composition greater than the Eutectoid as represented. Click Next to proceed to the next screen. Having understood what hardening means, let us take a look at tempering and understanding why hardening has to be followed tempering. Tempering is a process done subsequent to quench hardening. Quench hardened parts are often too brittle. This brittleness is caused by a predominance of martensite. This brittleness is removed by tempering. When the steel cools to above 40 degrees Celsius, after quenching, the part to be temperatured is heated to a temperature of 150 to 400 degrees Celsius. In this region, a softer and tougher structure, Trustite, is formed. Tempering results in a desired combination of hardness, ductility, toughness, strength, and structural stability. Note, alternatively, the steel can be heated to a temperature of 400 to 700 degrees Celsius. That results in a softer structure, known as sorbite. This has less strength than Trustite but more ductility and toughness. Quench hardening. As you can see in this diagram, in steel quench to a microstructure consisting essentially of martensite. The iron lattice is strained by the carbon atoms, producing the high hardness of quenched steels. Heating. Upon heating, the carbon atoms diffuse and react in a series of distinct steps that eventually form Fe3C, or an alloy carbide in a ferrite matrix of gradually decreasing stress level. Soaking. While soaking, the properties of the tempered steel are primarily determined by the size, shape, composition, and distribution of the carbides that form, with a relatively minor contribution from solid solution hardening of the ferrite. These changes in microstructure usually decrease hardness, tensile strength, and yield strength but increase ductility and toughness. Click Next to proceed to the next screen. There are 3 distinct stages of tempering. Click on each of the tabs to understand them in details. Stage 1. The formation of transition carbide and lowering of the carbon content of the martensite to 0.25%, 100 to 250 degrees Celsius. Stage 2. The transformation of retained austenite to ferrite and cementite, 200 to 300 degrees Celsius. After tempering, steel undergoes few changes in its microstructure. Let us now see how its structure changes. Tempering heat treatment allows diffusional processes where BCT martensite transforms to the tempered martensite, composed of the stable ferrite and cementite phases. The small white particles are the cementite phase and the matrix phase is called ferrite. Click Next to proceed to the next screen.